Hello guys! Today we are going to talk about titration. Now what is titration? Titration is a type of wet chemical analysis that is used by many chemists in order to determine the concentration of the unknown solution by carefully and gradually adding a reagent onto it. And that reagent is called the titrant. It has a known concentration compared to the unknown solution, which is called the analyte. Together, they form the basic components of starting up a titration.
February 27, we conducted an experiment, which is the experiment for Titrimetry. So today, we're going to discuss about our insights for the brief background about the experiment. So first, titration is done in order to determine the concentration of a dissolved substance in terms of the smallest amount of reagent added. In this experiment, titration was done in order to know the molecular weight of an unknown acid. So, through this experimentation, titrimetry, it helps the researchers to physically witness how titration works. It also helps the researchers or the students to easily witness the concentration of the analyte. Fourth, it also plays an important role or a vital role in our safety. Last, many real-life uses of titration are used each day, especially in the medical world and labs.
For the methodology, it is separated into three parts. First, the preparation of NaOH stock solution. Second, standardization of NaOH titrant. And third, the unknown analysis. For the preparation of NaOH stock solution, first, boil 1.1 liter solution of distilled water. Then, prepare approximately 0.1 mole of NaOH solution by weighing NaOH. Afterwards, dissolve the NaOH pellets and dilute to volume using volumetric flask. Filter the solution when cloudiness of solution is observed. Then, store the solution in a reagent bottle with its cover. For the standardization of NaOH titrant, first, transfer approximately 0.6 grams of KHP into a weighing bottle. Dry it in an oven for at least 1 hour. Cool in a desiccator for 30 minutes. Afterwards, weigh out 0.20 grams of triplicate measurements of KHP in a 250 milliliter Erlenmeyer flask. Then, prepare 250 milliliter pre-boiled distilled water. Transfer it in such a way that the water washes down any adhering salt crystals on the wall. Add 2 to 3 drops of phenolphthalein as indicator. Titrate using the NaOH solution prepared in Part A. The endpoint is signified by the appearance of the faintest pink. Record the volume of NaOH consumed by the KHP sample. Repeat the measurements in 2 more times and report the mean, standard deviation, and percent relative standard deviation for the triplicate measurement. For the unknown analysis, label 1 weighing bottle for storage of your unknown sample to be analyzed. Then, weigh out 0.10 grams of triplicate measurements of a known sample in a 250 milliliter Erlenmeyer flask. Prepare 50 milliliter of pre-boiled distilled water. Transfer it in such a way that the water washes down any adhering salt crystals on the wall. Add 2 to 3 drops of phenolphthalein as indicator. Titrate using the NaOH solution prepared in Part B. The endpoint is signified by the appearance of the faintest pink. Record the volume of NaOH consumed by the KHP sample. Calculate the molecular weight of the unknown, considering that the titration of diprotic acid was complete. Repeat the measurements in 2 more times and report the mean, standard deviation, and percent relative standard deviation for the triplicate measurements.
Guide questions. Number 1. Why is the water boiled in the preparation of NaOH stock solution? It is boiled to simply avoid the formation of carbon dioxide, which can affect the measurement accuracy. Number 2. Define primary standard and what is its purpose. Primary standard is the calibration of other standards, referred to as the working standard. Its purpose is to determine the concentration amount of a solution with definite accuracy. Number 3. Why do we have to pre-dry the samples and the standards? If a moisture is left resting in the samples, it will affect its rate of chemical reaction and will cause error in measuring the sample's weight. so it's better to pre-dry first for a better chemical analysis. Number 4. What will be the effect had there been any bubble formation inside the burette? Bubble formation in the burette may cause an added volume to your reading, thus contrasting to what the accurate measurement you're supposed to get. Number 5. Why does phenolphthalein switches colors in acid and base media? Phenolphthalein is a weak acid. In titration, it undergoes ionization to turn it into a base. Its hydrogen ions are actually stripped off of it when in contact with NaOH, which is actually the weak base, thus giving off a pale pink color, indicating that the phenolphthalein is no longer concentrated. Now what we see here is the chemical structure of phenolphthalein. What is phenolphthalein? Phenolphthalein is actually the indicator of the analyte's acid-base concentration. It is the one that gives off that pale pink color you see.
Now we're going to discuss about the data and results of the experiment for titrimetry. So for the letter A, the preparation of NaOH stock solution. First, we need to find the atomic weight of NaOH. In order to get that, we need to find the atomic weight of each element, which is the sodium, oxygen, and hydrogen. And we will add these three to get the atomic weight of sodium hydroxide. And after that, we will multiply it to 0.1 mole of NaOH in order to get the answer, which is 3.9997 grams of NaOH. And we're going to round it up. So the answer is 4. So in every 0.1 mole of NaOH, there is 4 grams of NaOH. For the letter B, the standardization of NaOH titrant, today we're going to find the mean of weight of KHB, the mean of the initial volume of NaOH, and the mean of the final volume. So in order to find the mean, the formula of mean is the sum of the terms divide or over the number of the terms. So in every trial, there is different data. So for the weight of the KHP or the potassium hydrogen phthalate, for the trial 1, there is 0.2080 grams. For the trial 2, 0.2, and for the trial 3, there's 0.2 grams. And after that, we're going to add the 3 trials and divide it to 3, or the number of the terms. Same as the initial volume, we're going to find the mean of it, so the answer is 50. And for the mean of final volume, the answer is, or the mean of it is 45.9. So for the true value of NaOH, the formula of it is initial volume over the final volume. So the trial 1, the initial volume of it is 50 divided by the final volume, which is 44.7. So the answer is 1.119. For the trial 2, 1.111. And for the trial 3, 1.042. So for the molarity of NaOH, since they all have the same data, for the trial 1, 2, and 3, the answer is 0.91 mole per liter. We move on to the mean molarity. So for the mean molarity of trial 1, there is 89.37. For the trial 2, 90.08. For the trial 3, there's 96.04. In order to get the mean, we need to add these 3 trials and divide it to the number of the terms, which is 3. So the answer is 91.83 mole per liter. For the standard deviation, the formula of it is square root of each value from population minus the mean and square root of it divide or over the size of the population. So the answer is 2.991097903, and we round it up, so the answer is 3. And for the relative standard deviation, the formula of it is standard deviation over the mean times 100. So the answer is 3.266,90624, and we round it up, so the answer is 3.3%.
So for letter C, we are to find the value of each trial's weight sample, the initial and final volume of the NaOH, and the true value of NaOH. So then, we've got the weight sample of trials 1, 2, and 3, and they are all equal to 0.10 grams. The initial volume of each trials are the same, which is equivalent to 50 ml, but for the final volume, trial 1 is equivalent to 49.5 ml, trial 2 is equivalent to 45.5 ml, and trial 3 is equivalent to 48 ml. Now, in order to find the true value of each trials, we are to divide the initial volume to the final volume. The results are as follows. Trial 1 is equals to 1.010 ml, trial 2 is equals to 1.098 ml, and trial 3 is equal to 1.042 ml. For the molecular weight of H2X, we've calculated for trial 1 and 2, which is equal to 49.59 grams per mole and 47.98 grams per mole for trial 3. For the mean of H2X, we are to add the values of H2X molecular weight of all the trials and divide them to 3. So we can get 49.05 grams per mole. To calculate the standard deviation, we use the formula of square root of summation of each population subtracted by population mean, all enclosed in parentheses with the exponent of 2 divided by n. We substituted the given values to the formula and we got 1.9003. And finally, to get the percent RST, we divided 1.9003 with 49.05 and multiplied the answer to 100 to give us the value of 3.874.